Okay, today we're going to take some notes on rotation. We're going to start this unit with kinematics the same way we started the year with kinematics. Kinematics is the study of how things move and not why. Why comes later. So everything we've focused on so far this year has to do with objects that are moving in straight lines or changing directions in such a way that you could still have their path be approximated by a curved line at the very least. And so we've dealt with motion like this. Whee! Okay, so that kind of motion we can evaluate easily. Where we have an object moving in line, we can talk about displacement, velocity, acceleration. What we're moving into now is looking at a situation like with this top. If I look at a point on the top right here and want to talk about its motion as it spins, we could still use some of the tools we've already used. But if I want to talk about the top as a whole, well, it's not going anywhere. It's the center of the top isn't moving at all. But we still can talk about its spinning. And so now everything we've talked about with lines, we're going to translate into something, a spinning object. So we're going to split this and talk about linear motion and rotation. And so when we talk about how far something goes in a straight line, we call that a displacement. We usually, or at least I use the variable x as my default. In rotation, when we're talking about the displacement of something moving in a circle, so let's say I spun the top and I had this high-speed camera and I was interested in how far it rotated. Instead of looking at a line, we're looking at an angle. Just like in the treatment of angles we've done so far this year, displacement is with theta. So here we have x is displacement, rotation, I'll do that set up that way. X is displacement for linear, for rotation theta is displacement. And that measures how far. For velocity, we know linear velocity is change in position over time. That's the average linear velocity. For rotation, again, we can talk about change in position over time. Now, when you talk about rotation, we use theta now instead of x. And so we talk about omega. This is a lowercase omega. If you're familiar with omega, it's probably the one that looks like a horseshoe. This is a lowercase omega. And it's the change in angular position over time. So this is angular displacement, is really, I guess, change in theta, delta theta. Angular velocity is the rate at which theta is changing, the same way that linear velocity is the rate at which position is changing. That leads to acceleration. I bet you know where this is going. So an average or a constant acceleration is change in velocity over time. Angular acceleration is alpha. Alpha looks like a fish, kind of. A lowercase alpha. Like that. Equals a change in angular velocity over time. Okay, so now we have the definitions of the kinematic quantities for rotation and how they relate to the kinematic quantities we know for linear motion. Since they have direct relationships, all the kinematic equations you already know for linear motion can be translated into rotational variables. So let's do that now. Alright, where to begin? Let's start with the acceleration equation rearranged, which becomes Vf equals Vi plus At. If we rearrange the alpha equation, we get omega f equals omega I plus alpha t. Alright, let's do the position function. X equals Vit plus 1/2 At squared. So for rotation, that becomes theta equals omega 1t plus 1/2 alpha t squared. So just make sure you're not losing track of what this is all about. If you knew how quickly an object was spinning to start, you knew how long the object was spinning, you knew the rate of change of the object's rate of spin, you could figure out how far it travels in, oh, and again, just like back in the day, we should remember that this is the change in the position, so this is the displacement. You can figure out the displacement of, the angular displacement of a spinning object using this equation. Okay, Vf squared and then for this one, so those are all the good basics. So those are your basic kinematic equations for rotation. Before I move on, let's talk about units quickly. So we know that displacement for linear is measured in meters, velocity is meters per second, acceleration is meters per second squared. Now for theta, what we've used up until this point has been degrees. And so you could use degrees for this and it would work out, but actually a more useful unit of measure for theta in angular kinematics is the radian. And I'll explain why in just a minute.